All right, so 10H is Newton's method. Does it come up in the exam? Yes and no. It has been coming up as a pseudocode question, so a multiple choice question. You do need to know it as part of your study design, just like bisection method from last year. You needed to know that as well. That is examinable. Newton's method, what is it? It is a recursive algorithm. You can fill that in. You just need it's a formula. You just apply it. And the algorithm is used to find or to approximate x-intercepts. That's all it is. Kind of like your bisection method. Very similar. The more you do the process, the more you repeat that process, the algorithm, the more accurate the solution is. So there's a difference between bisection method and Newton's method. How does it work? Very simple idea. Newton's method, it does or finds the x-intercepts by simply finding the tangent. So uses a tangent line, means you need the derivative. Uses a tangent line at any point. So you start off at an x value. Okay, you start at an x value, say xn. And then afterwards, with that tangent line, it must eventually cross the x-axis. When it crosses the x-axis, that becomes your new x value for the next tangent point. Does that make sense? Okay, so I'm going to draw a picture so you can visualize it. But finding the x-axis intercept is the second step of the tangent line. Then with that x-axis intercept, you're going to use that new x-coordinate to find the next x-axis intercept of the tangent line. So here it looks like something like this. And I've got a Desmos version here for you to see. And you can type that up, or if you have the digital version, you can click on it and it will take you to the Desmos creation that I made. But this is what it looks like as an example. Say you got a quadratic graph that looks like this. Actually, no, I should get some x-intercepts. Let's say it looks like that. We know the x-intercept is somewhere here, right? And we usually solve it by factorizing it, and then we solve it for using null factor law. But say you get an equation where you can't factorize it, and you don't know how to solve it, right? It doesn't work out nicely. So what Newton's method is to say is you pick out an xn, so initial point, touches this point, right? Then must have a tangent line that touches that point. When it touches that point and it has a tangent line, well, that tangent line has to also touch the x-axis. This x-axis now becomes your new x-coordinate to do it again. So this now becomes, let's call it xn plus 1. So it's the next one. And with that point, you then connect it back and you say at this now, at that particular point at xn plus 1, you get another tangent line. And with that tangent line now, can you see how it's closer? It's a lot better than the first one. So the first one was slightly steep. But as I get to the second x-intercept, now the x-intercept of the second tangent line is a lot closer to the actual x-intercept that we want. And so hence, the more you do this, eventually the tangent line gets really close to exactly closer and closer, a better accuracy of the approximate point of the intercept. That's the idea. Okay, so it's a very simple idea. And the formula looks nasty. It looks nasty, but if you read it, process gets repeated until the y value is as close to 0. Why 0? Because it's the x-axis intercept. So the y value, each x value has a y value. The closer the y value to 0 is, the closer it is to the x-axis intercept. Okay? If you look at the formula, it looks nasty, but it's actually really just the derivative and a straight line equation rearranged. Okay, so you know your y equals mx plus c? That's the tangent line. So then m is the derivative. So you can say it's f dash of x. That's where they're getting, that's where they're getting this from, right? To get the y value for x, that's just f of x. That's what this represents, right? And then to find the y-intercept, if you rearrange all of this, you get c is equal to f of x minus f dash of x times xn. Okay? And that's what you're seeing here. That's just a rearrangement of that equation. And so they just rearranged that equation to find the x-axis intercept of the new equation. That's simply what it is. Yeah? So, let's delete this. This formula will be on your exam. And that, I don't know if they usually write Newton's method or not, but that is Newton's method. It's just the algorithm that to find the next x-intercept, you use the previous x value. This tells you the y value. This tells you the gradient at that value, at x equals to xn. Okay? So the formula tells you the new x-intercept is your old x-intercept, or x value. Take away the y value divided by the gradient. And that's the formula you can use in an algorithm. So you can use a spreadsheet. You can do recurrence one on your calculator. It's up to you how you want to do it. So I used that same formula in Desmos to create what you're going to see next. This is what it looks like. So I chose an example. I said, let's do x squared minus 2. Okay, that's my graph. And this is, where's my Desmos graph? That's not Desmos. Where's my Desmos? Newton's method. Here we go. So I use the same formula. I wrote f of x equals x squared minus 2. There you go, you get your red curve. I have g of x, which is technically the derivative. And then here is just a f of a. So for x value, whatever I choose to sub in, f of a, which is subbing a into that point. Okay, and a is a variable. So a can be 4, which in this case, when a equals 4, y value is 14. So that's my first point. With that first point, I got to sketch a gradient line. So tangent line, what we've done in 10a and 10b, yeah, to find the tangent line. So here I wrote, okay, well let's find the tangent line, which is that y equals mx plus c thing that we were talking about, rearrangement. There's my derivative. So derivative at that point times x, so mx plus, and how I told you I rearranged c before, that's your f, that's the y value minus the gradient times the x value at that point. Yeah, so this looks confusing, but I pretty much just did y equals mx plus c. That tells my tangent line. Then the next one is, well, how do I find the y-intercept? Well, this one, if you want to find the y-intercept, let y equal to 0, rearrange the equation, find x, and that's what you get. Okay, so this is the x value whilst y is equal to 0. All I did. Yeah? And what this means is, visually, you can see what happens here. So at 4, the x-intercept is 2.25. So that means the next one, if I want to find the next tangent line, my x value now is 2.25. So I change from 4 to 2.25. And now, at 2.25, that's my new tangent line, and that's my new x-intercept. And then I do it again. So I say, okay, well, that's my new x-intercept at 1.56944, and I type it in again. So that's what the algorithm is doing. The algorithm is just simply finding for every new x value or x coordinate, the x-intercept, I'm subbing in to find the tangent line and finding the x-intercept. Obviously with Desmos, it's not nice and visually. You have to somehow replicate that in your CAS. So you can either do it through an algorithm or you can do it through a spreadsheet, but the formulas are pretty much the same. What do you need for the exam? They won't get you to do that in the exam. They'll just get you to read a pseudocode. So they'll give you a set of codes and you should be able to read through something like this. Okay, so it might be this, but in a pseudocode form, and you should be able to read it and go, oh yeah, this must be Newton's method. It is finding the x-axis intercept, and they might say after 4 iterations, A, B, C, or D, which one's the correct answer. Okay, so you'd have to do this 4 times. So I've done it twice. If I did it 4 times, what would my x value be? That's what a typical exam question so far has been. Whether they change it this year or not, I'm not sure. But so far, what we've seen in the last 2 years is it's become a pseudocode question. So you only need to understand the theory at the moment. So if you understood what I just described, that's all they need. If you have UDFs, you can easily answer those questions in the exams. If you don't, then you just got to learn how to do this algorithmically on your CAS. Okay? So my notes I've given to you here. we can see the x-intercept here is at currently 2.25. So 2.25. You start with x equals 4. And use your calc to find the equation of a tangent line, which... let's go back to my cas. Here we go. Let's go define f of x is equal to x squared minus 2. Let's find the tangent line. So menu, calculus, number 9, tangent line, f of x at x equals to 4, and I get 8x minus 18. Okay, and if I wanted to find, so at x equals 4, then f of 4 gives me 14. So this one is 14. So there's my coordinates, 4, 14. What's the derivative at that point? Well, I need to find the derivative here. So here we go. Actually, you don't need to do the derivative if you're doing the spreadsheet. But if I do the derivative, let's go f of x. Let's call it g of x. Control var means you store it into g of x. And I go g of 4. So gradient's at 8. Okay, which makes sense. Gradient of 8. And here we go to find the x-intercept where you let y equal to 0. So you can essentially say solve 0 equals 8x minus 18, comma x, 9 over 4, or 2.25. So the first one is 2.25. And then you follow the same thing again. So this is doing it through the calculator page. Okay, you can just keep repeating that. So if it's an exam, you can do this. And if they say 3 iterations or 4 iterations, you'll do that 3 or 4 times. Okay? Or you could set up a spreadsheet. So if you do it on your CAS, you can add on a spreadsheet to find the functions that I had before. So you can have x coordinate, define the f function, define the derivative function, and then you can work through the same idea. Okay, and then you can pull down the spreadsheet. So on the sheet, I've given you a bit of guidance if you want to practice it. You can go through this page, and I kind of guide you through how to do that. But there's multiple ways of doing it. Easiest way is UDF. But like I said, the theory is probably more important. Okay, so there's multiple ways on how you can figure out the x-intercept and then follow on. So again, if I want to do it again, you do f of 9 on 4. This is by hand, by the way, or by the CAS calculator page. So then you get, maybe I should leave it as exact value, 49 on 16. And then you can do the same thing again. Menu, calculus, 9 tangent for f of x at x equals 2, 9 on 4. And then solve equals to 0, comma x. And you get your next one. You follow on. So, like I said, if you're doing it as a multiple choice, it's only 3 to 4 iterations. You can do that. If you can be bothered to set up a spreadsheet, you can do it that way too. Quickest way is UDF, but eventually they will take that off. So you are in a comfortable year where you can still use UDFs. Next year they'll be removing it. So it's up to you which one you prefer. So if you prefer doing a spreadsheet, then you add on control, page, go list in spreadsheet. And we'll start off with, we'll call this x. Let's call this f of x. Whoops. Why can't we call, oh, that's right. Let's call it, what do we call it? Y value. Let's call it y equals to f of x, column reference. There's a variable reference, I think. Oh, which one is it? I think it's variable. Let's see if this is true. F of 1, F of 4. Yeah, okay, it works. So you can see how I'm setting it up. Because I called it f of x before, x is the variable, so that's my variable. So when I put 4 here, I get 14. And all you need to find is the y-intercept, and this is where you can type in Newton's formula. So Newton's formula, you just need the next x-intercept value is the old one minus the y value divided by the gradient at that point. So if you want, you can call this g, actually let's do m for gradient. And this would be g of x, which I think I defined as the gradient before, I'm pretty sure. And that would be variable reference. There we go. So you got your x value, y value, gradient value. So the next one you can now use Newton's formula and then copy it all. So Newton's formula says this will equal to, what was it again? It was previous x value. So it'll be A1 take away. What's this? Fn. So B1 divided by C1. Circular. Why is it circular? Where did I go wrong? Should be 4 take away 14 divided by 8, isn't it? What did I do? 4 take away 14 divided by 8. Yeah, it's correct. What did I do? CA1. No, go wrong.
You know what I used to do? Yeah, I used to do it on foot, the same we would have to do it.
It's meant to work.
And I just put it in the cat. He just spit out the answer. And then I get full marks.
Why is it circular argument? Doesn't make sense. This was equal to g of A1. Oh, maybe because I wrote variable reference before. So maybe this is meant to be f of A1. And that's 4. So then this one should then be A1 minus B1 divided by C1. Huh? I need to play around with this again now. Give me a second. All right, it's re-recording. All right, for those who want to do the spreadsheet, I've defined it now. So follow the instructions on my notes. You define the function, which we had x squared minus 2. Then we need a derivative. So I called it define g of x equal to the derivative, because that's going to give you the gradient value. And then finally, I define h of x as Newton's method. So Newton's method says take the x value that you're thinking of, so your initial x value, minus the y value, which is f of x, divided by the gradient at that point, so g of x. So that's Newton's method. Then I go to my spreadsheet, and I'll call this I for intercept. It was bad that I called it x before and it got all confusing. That's why it was a circular argument. Y for the y value, so I for intercept, and then m for the gradient. So you can see I start off at 4. To find the y value, it's equal to f of a1. So that's finding the y value. Next one is equal to find the gradient of that value, do g of a1. So that gives me the gradient. And then to get the next intercept, that's my Newton's method. So h of a1. Okay, so it's saying find the next intercept using the previous x value. So if I do that now, I get my 9 and 4, which was 2.25. And now all you have to do is copy this pattern all the way down, because this one says find the y value of this. This one says find the gradient of this. So if I pull this all the way down, which you can do menu, data, field, and you can drag it down for how many iterations you want to do. So I can drag it all the way down to 11. So that is the pattern now. And then this one I need to drag what down as well. So I got to say data, feel if I drag down to the 10th iteration, I get my exact values. And obviously, if you change your mode to decimals, it will change it to decimals as well. So that could be another way to do it. Probably faster if you have a bit of time. Fastest way would be, like I said, UDFs. They would literally do all this and spell it out for you. But that's Newton's method. So you just need to know the theory. It's the tangent line, get the x-intercept, use that x-intercept to find the next tangent line, and you follow on. And the algorithm follows. Okay, but there's 2 ways to do it there just then. I just showed you initially how to do it just on the calc page. It's a bit tedious, but if it's only 2 or 3 iterations, it's pretty doable. And if you have time, you can set up a spreadsheet, and you can pull all the way down, and you can get the number of iterations. Okay? All right, team, I think that's about it. That concludes chapter 10. That's the final bit. Oh, actually, sorry. One last bit. There are some caveats to Newton's method. 2 parts, which is quite logical, where it doesn't work. If you think about it, it relies on the tangent line. If the tangent line happens to be parallel, like the maximum, then it won't have any x-intercepts. So it wouldn't work. Number 2 is that it could be an oscillating sequence. So it means that the tangent at a particular point gives you an x value that gives you another tangent point, x-intercept, that gives you another tangent point that brings you back to the same point. So this line, if I chose x here, is my tangent point, the x-intercept is over here, it happens to give me another tangent point, but actually that tangent point has an x-intercept back to the very first one. So this is an oscillating scenario. So you never actually get closer to the x-intercept. So there are 2 caveats to it. I think there's only one time I saw this somewhere. It was either in a SAC from another school who asked, what is the flaw of Newton's method? And you just had to name one of those 2 or explain it. Other than that, I don't think I've ever seen it afterwards. But keep in mind, Newton's method is new into the course. So hence, maybe that's why they haven't put in too much into the exam. Doesn't mean it won't be in this year's exam, but it's just worthwhile knowing 2 of the caveats there.
Oscillating sequence. Is there a way you can know which x value will give you an oscillating sequence? Okay.
At least not to my current knowledge.
So they said, I got the exam, I get a random x value and just find the x-intercept using Newton's method. You just gotta hope it's not one of those.
Well, you would probably pick it up as you do it. So if you use UDF, then you'll just see the numbers oscillate. Yeah. If you do it by the 3rd point, you'd probably know. So you start off with a point, go to the 2nd, and then by the 3rd point, you would know that it's oscillating. It's just more about explaining why. So I don't think they'll give you one that you'll get. They'll probably ask you what's a limitation to it. So name a limitation.
And also, if there's multiple different x-intercepts here, or there's only 3 there, if you want to find, say for example, the rightmost one, how do you ensure that you're getting that x-intercept and not the other 2?
I don't think you could. So unless you have a graph, then you'll then pick the most rightmost, because then you know the tangent line, the x-intercept will get closer towards the left because it's a positive gradient. If they don't have a graph for you, then you're blindly relying on the fact that the y value gets infinitely small. So it will be an x-intercept, you just don't know. Yeah. And I guess it's usually used as an approximate that you know it's somewhere, you just don't know what that approximation is. And I think that's what your calculator does. You know, on your graph setting, when you choose to find the x-intercept, and you choose between 2 bounds, I think that's what it's doing. It's just playing around with getting it smaller and smaller. Yes. There we go. That's Newton's method. So theoretically, you just need to understand limitation is a small pit, but can be sackable. At least I remember seeing it or reading it somewhere. And method-wise, there's 3 ways to do it. You can do a spreadsheet. You can do it just typing on the CAS a couple of times, or you can use UDF. All 3, you probably only need about four iterations from memory. Usually they only get you to do 4. It's really easy with the UDF, so I doubt that the examiners will make it so that you have to do like 10 iterations. Okay. All All right, team, I'll stop there. If you want to, you can look, if you're familiar with reading pseudocode, if you've done systems or something, you can have a look at the 2023 exam. That's an example of a pseudocode. And you just got to pick the correct answer based on how many iterations it's asked you to do there, which looks like 3 iterations.